4th International Physics Olympiad year 1970 IPHO. Problem number 4. A spherical aquarium filled with the water is placed in front of a flat vertical mirror. The radius of the aquarium is r, and the distance between its center and the mirror is 3r. A small fish, which is initially at the point nearest to the mirror, starts to move with the velocity v along the wall. An observer looks at the fish from a very large distance along a horizontal line passing through the center of the aquarium. What is the relative velocity v real at which the two images of the fish seen by the observer will move apart? Express your answer in terms of v. Assume that the wall of the aquarium is made of a very thin glass. The index of refraction of water is n equal 4/3. Solution for problem number 4. So first we have to check what happened to the direct image of this fish when it's moving. After that check what happened to the mirror image of this fish when it's moving, and after that compare them. So first let's check what happened to the direct image. In a small time interval delta t, the fish moves upward from point A, this one, to point B, this one, at a small distance d equal v multiplied by delta t. Since the glass wall is very thin, we can assume that the rays leaving the aquarium refract as if there was a water-air interface. The divergent rays undergoes one single refraction as shown on this figure from the first virtual image of the fish. The corresponding vertical displacement A1, B1 of that image is equal to the distance D1, this one, between the optical axis A and the ray B1, between this one and this one, which leaves the aquarium parallel to A. Since the distance D and the D1 are small compared to radius R, we can use the small angle approximations. So we have sine alpha approximately equal tangent alpha, which is approximately equal to alpha in radians. So here we have angle alpha, this one, angle gamma, this one, and the two angles beta, this one and this one, which are equal to each other. First we have d1 equal approximately r multiplied by alpha, d approximately equal to r gamma, alpha plus gamma equal to beta, and due to Snell law we have alpha approximately equal n beta. Now, using equations from 1 to 4, we find that the vertical displacement of the first image in terms of d equal this one, and respectively its velocity v1 in terms of v is this one, v1 equal n over 2 minus n multiplied by v. So that was comparison for direct image. Now let's go to mirror image for the same fish. Now consider a refraction from the mirror. The rays which are first reflected by the mirror and then are refracted twice at the walls of the aquarium form the second real image. See this second figure. It can be considered as originated from the mirror image of the fish, which moves along the line A', B' at exactly the same distance d as the fish do. The vertical displacement A2, B2 of the second image is equal to the distance d2 between the optical axis A and the ray B2, which is parallel to A. Again, using the small angle approximation, we have d prime plus d equal to 4 times r delta, this one. d2 equal approximately r multiplied by alpha, and following the same derivation of the equation 4.5, we obtain that d2 equal n over 2 minus n multiplied by d prime. Now, using the exact geometric relations, we have delta equal to alpha minus 2 beta, and the Snell law 4.4. In the small angle limit, we finally express d2 in terms of d. So we have d2 equal n over 9n minus 10 multiplied by d. And the velocity v2 of the second image is in terms of v equal this one, which is 2 over 3v. The relative velocity of the two images is v relative equal v1 minus v2 in a vector form, and since vectors v1 and v2 are oppositely directed, one of the images moves upward and the other downward. The magnitude of the relative velocity is v1 plus v2, which is 8 over 3v. So that was a solution for problem number 4.